In fact, in 2005, Saugenik, Dodds, and Watts carried out an interesting online experiment that mimicked some of the features that we were discussing about YouTube video popularity. So let's very briefly take a look at this experiment. This was a controlled experiment involving a large number of participants by the standard of sociology study back then, 14,341 participants, and there were 48 songs from unknown bands. And what they did is to show these 48 songs in different orders and presentations to these 14,000 plus participants, and then tally the download numbers. So they're going to look at the popularity by the download numbers in 4 different scenarios, depending on 2 different criteria. One is they will show either random ordering of these 48 songs or a descending order by the current download number. Then for each of these 2 ordering, they will show either the download number or hide them. So they're altogether 2 by 2, 4 possible scenarios. And as you can see, as you go from random to descending order of download number, the peer influence power increases. And as you go from hiding the download number to directly showing the specific number, you also increase the peer influence. So you got 4 scenarios with increasing peer influential power. And the question they asked is, what about the download number in the end of the experiment? It turns out that the vector of those download numbers, M1 up to M48, we got 1 vector for each of the 4 scenarios. See that a more social influence always leads to a bigger spread in the download numbers. We can measure that by variance, we can measure that by some kind of L1 norm of this vector. It also increases the unpredictability of the success of these songs from unknown bands. Now, in the least influential power scenario, we can take that as the benchmark, because in that case, the ordering of the songs are random and the download numbers are hidden. And then you see that as we increase the social influence through the other 3 scenarios, it becomes less easy to predict which songs will be more popular. The really good one and really bad ones, okay, the top and bottom of the vector in this benchmark scenario pretty much stay the same, but what's in between often change place a lot. So now the question is there some kind of general theory about these phenomena, including the impact of knowing what others have done in front of you? So we're going to try to build a very simple model on sequential decision making in a crowd. You can effectively think of that different people forming a linear topology, a line. Okay? You get to observe, so you are here, what happened before you, and then you're going to make a decision for the future generations to observe. And in these sequential decision-making models, each person gets a private signal and then releases a public action. The private signals will remain unknown to the future users, but the public actions will be staying there for them to see. And this creates an information dependence, because what you would be doing would in part depend on the information that you can collect by observing what others in front of you have done. And we'll see that such an information dependence, in contrast to the independence assumption in rating averaging on Amazon, will lead to a cascade. It breaks down the wisdom of crowds and leads to basically a cascade where no matter what the private signals are in future generations, they will always follow the same action as the crowd before them have taken. And we see such cascades is actually easy to form, can become very large, can be wrong, and yet can also be fragile, can be easily broken. And the way we're going to talk about this model is through a thought experiment. I want to highlight that this thought experiment assumes that people react in a rational way. But in reality, people don't. And that's one of the difficulties of understanding social networks, is because most of the theories that are tractable that we build assume that human beings behave in the way the model asks them to behave. But having said that, and knowing that this thought experiment in reality actually sometimes doesn't work out the way the theory predicts, let's still go through it because it offers interesting insights to chain reaction in the crowd. So we've got people lined up here. Okay. And then they go up to a table. Okay. And beneath the table there is a piece of paper with number 0 or 1 written on it. And that's the correct number, but you don't get to observe the correct number. The private signal each person gets is a probabilistic version of that signal. So whether the signal is 0 or 1, you're going to flip a coin, a loaded coin with probability p, it will remain 0 or 1, the true number, but with probability 1 minus p, it will flip. So the 0 becomes 1, 1 becomes 0, and your private signal therefore is incorrect. Now we're going to assume that with equal chance, half-half, the true number is 0 or 1, but actually that doesn't quite matter, as we'll see later in the formula. However, we do insist that the probability of each private signal is better than half, meaning it is more likely to get the correct number than the incorrect number. That we will assume. Let's also assume that these p's, which in general can be different for each individual indexed by I, are all equal. Later in the next segment of the video, we'll talk about briefly what would happen if they are indeed different. Now, observing this private signal, each person would think, what would the correct number be? And let's assume each person is a rational Bayesian agent. It says that, well, since there are two numbers, I guess I have to guess one. Whichever number has a higher chance, more than 50% chance of being the true number, I will guess that and write it down on the blackboard. Okay, the first user may say, I guess the true number is 0. Second may say, I guess true number is 1, and so on. So later people can observe all the previous history of the public actions, but not the private signals. So that's the setup of this very simple thought experiment. And we wonder what would happen. Now suppose you are the first person going up to that table and the blackboard. Let's assume that you see 1. That's your private signal. What would you guess? Well, knowing that P is strictly greater than 50%, you know that with it's more likely the true number is indeed 1 as opposed to 0. So your public action is just 1. Similarly, by symmetry, if you receive 0, you write down 0. So this is private signal, and this is public action. And the public action is the same as private signal. Let's give a symbol X to the private signal, Y to the public action, and 1 index the first person. So Y1 equals X1. That's very simple. What about the second person? Now the second person coming up to the table and the blackboard sees on the blackboard a number 0 or 1 from the first one. That's Y1. Now even though the second person doesn't know what is X1, she can, however, reason through what the first person had reasoned through. So she knows that whatever Y1 is, it must be equal to X1, because that's what a rational person would do. And therefore the second person actually knows what is X1, because by logical reasoning, she knows that whatever y1 is, that's also x1. So she has both x1 and x2 now. If these two are the same, clearly y2, her public action by the second person, would be the same as they. So if they're both 1, then this is 1. Both 0, then this is 0. What if they're different? x1 is not x2, 0, 1, or 1, 0. Then y2 basically can be whatever. The second person say, well, then I have to just flip a coin and decide. Okay. So there are different variations of this experiment, but in ours we say that if x1, x2 are different, again, x1 really is y1, but the second person knows x1 equals y1. If they're different, then I'll just flip a coin. In other words, y2 may be 0, maybe 1, each with probability half. So we can write this down, for example, as the following. We say that the probability that y2 equals 1 given x2 is 1 and y1 is 1 is 100%. Similarly, the probability this is 0 given both are 0 is 100%. But the probability that y2 is 1 given x2 is 1 but y1 is 0, or the other way around, is 50%. The other 50% is that I'll write down y2 is 0. That's another 50%. All right, that's the second person. So far, so good. What about the third person? Now here comes the tricky part. And this is where, as we'll soon see, cascades start. The third person says that, well, I'm standing in front of the blackboard and I can see two public actions, y1 and y2. I also get my own private signal, x3. So I got 3 signals here, and I have to make a decision through Bayesian analysis of what should my y3 be. Now, if y1 is not the same as y2, okay, that means, again, that x1 and x2 cannot possibly be the same, because if they were the same, y1 y2 would be the same. Since x1 and x2 are not the same, and therefore I can pretty much ignore y1 and y2, because the last two users just got two different private signals. That doesn't tell me anything. I am back to the same shoe as the first user. Okay, here comes the beauty of the simplicity of this thought experiment. So anytime there's an odd number and an even number of two public actions being different, then the following person can just be back to the same shoe as that odd number user. Okay, back to the first user. But what if y1 equals y2? Okay, then let's see what x3 is. If that also equals x3, clearly my y3 will just follow whatever all these three numbers are. They are the three same number. But what if y1 equals y2 but differs from x3? Now, this is the scenario that is most interesting. I got two public actions from the crowd in front of me that conflict with my own private signal. Which one should I trust? Should I trust the two public signals? Should I trust my own private signal? Or should I equally trust them and continue flipping coins? Well, let's see what would happen. And the Bayesian thinking is basically the following. Just as what we did in lecture 5 with Amazon average rating, we're trying to figure out what is the probability in shorthand notation P that the true number is 1 if I have observed the following. y1 is 1, y2 is 1, and yet my x3 is 0. This is the shorthand notation. Okay, probability that the true number is 1 conditioned on or given that y1, y2 are both 1s and yet my x3 is 0. Now, if this is bigger than 0.5, then knowing that we're just guessing between two numbers, I'll say the true number is 1, then y3 is 1. And that's amazing because this says I'll ignore my own private signal and go with the previous two's decisions. Okay? But if this is less than 0.5, then I will still be following my own private signal and do not depend on prior actions. If this is exactly half, then I'll be flipping a coin. So let's find out, is it bigger than half or not? By base rule, we know that this expression is the same as the following. The probability that the underlying number is 1 times the probability that if the underlying number is 1, you get y1, y2 being 1, x3 being 0. And divide by p of 1, 1, 0. One way to see this is that you can move this to this side of the equation, and then you can see that we're talking about probability that you observe 1, 1, 0, meaning y1 is 1, y2 is 1, x3 is 0, times the probability that condition on that the underlying number is 1. That is nothing but the joint probability that the true number is 1 and you get 1, 1, 0 as y1, y2, x3. And yet that's also what this expression is saying, right? It's the probability the true number is 1 times the probability that given the true number is 1, you observe 1, 1, 0. So then you can just move the expression from that over here in the denominator. But we also know we can rewrite this expression simply as, by the law of total probability, as probability that the true number is 1 times the probability that you observe 1, 1, 0 given the true number is 1 plus the other branching, which is the true number is 0 times the probability you observe 1, 1, 0 given the underlying number is 0. So now we are done. In order to find out whether this expression is bigger than half or not, we just have to evaluate this division. So let's just take a look at what the numbers might look like. In the numerator, the probability that the underlying number is 1 is, in our assumption, half. Okay, fine. Times this probability. If the underlying number is 1, what's the chance you see 1, 1, 0? Well, there are two possibilities. One is x1 and x2 are both 1s, and then x3 is 0. The probability of that is p times 1 minus p. But don't forget there's another chance that the underlying numbers is x1 is 0, that is 1, x2 is 0, but so happens the second user flipped the coin, and the coin flip shows that, to break the tie, you pick 0, you pick 1. So that happens with probability p times 1 minus p for the first two users. The third user sees 0, another 1 minus p, while the second user flip a fair coin, so with probability half, it will write down 1. So two possible scenarios leading to this observation condition on the underlying true number is 1. That's the numerator. Similarly, you can write down what the denominator look like. And then you can start canceling terms like p times 1 minus p, and then normalize them by 4, multiplying both numerator and denominator by 4, and then simplifying the expression. You see, you are simply doing a division of 1 plus p over 3. Is this bigger than half or not? Well, depending on what p is. But we know p is bigger than half. The chance of seeing the correct number for every one is the same, and they're all bigger than half. That means this expression is bigger than 1 plus half over 3, which equals half. So this expression is strictly bigger than 50%. And therefore, y3 will be 1. And therefore, even if you observe x3 being 0, different from the y1 and y2s, you still go with whatever y1 and y2 say. That means you ignore your own private signal. That means you have just started throwing out your independent private signal and following dependent on the previous crowd. That means you have initiated a cascade. Because as you can easily reason, the fourth user after you will see y1, y2, y3 all ones. And even if she gets a 0 as x4, the private signal for her, she will still follow you and write down 1. And therefore, on the blackboard, at this point, it will be 1, 1, 1, 1 all the way down. The information cascade starts. We say it's cascade because past this point, once 3 ones shows up, it will keep on going as 1. We say it's information cascade because the cascade starts because the third user ignored her own private signal and followed the information obtained by observing the previous 2 public actions. Of course, we were following this track of cascade of ones. It could also be a cascade of zeros. If the first 2 users both write down 0, the third user would write down 0 no matter what her own private signal x3 is. Okay. So this starts the cascade, and we wonder how likely this will be. Well, let's see what's the chance of starting a cascade. We know that as long as y1 equals y2, cascades start on user 3. So if we don't want a cascade, the probability of no cascade means that I want the first 2 to be different. The first x, y1, y2 to be different. What's the chance that they are different? For example, if x1 is 1, that means y1 is also 1, but x2 is 0. Okay. Then the 2 will be different. Okay, so what's the probability of that? That is that's p times 1 minus p times half. Okay. Now, what's the probability that the other scenario, y1 is 0 and x2 is 1? Then the probability is also p1 minus p times half. Okay. Again, let's look at the chance that x1 is 1. That's probably p, okay, given the underlying 2 number is 1. Okay. And we want y2 to be different. That means we want x2 to be different. That's the chance 1 minus p being 0. And since they are different, the second user will flip a coin, and with probability half, it will actually indeed write down y2 that is different from y1. That's why we write down this expression. Okay. But by symmetry, it could also, instead of being 1, 0, it could be 0, 1. And it's the same expression. So the total chance, assuming the underlying real number is 1, is the sum of these two, p minus p times 1 minus p. But of course, the underlying true number could be 0 too. If it is 0, we carry through the exact same calculation by symmetry. It's also p times 1 minus p. So even after unconditioning against the underlying true number, the probability of no cascade being meaning that y1, y2 are different, that probability is p times 1 minus p. Now, what's the probability of cascades of ones when we call the up cascade versus probability of cascade of 0, the down cascade? Well, by symmetry, we know that they are both half of 1 minus the probability of no cascade. Okay. So the probability of having definitely some cascade is 1 minus p times 1 minus p. And the probability of either up or down cascade is that expression halved. So the probability of no cascade, the probability of having some cascade, and the probability of either up or down cascade. Now, this is the argument for the first two users, with implication to the third user, whether cascade starts there or not. Well, now, what about running this for a longer period of time? For example, what's the chance that there is no cascade even after 2n users? After 2n users. Why do we use 2n? Just to simplify the expression a little bit, because we know that it's always a pair of two users, odd number, even number, odd number, even number, that may initiate a cascade just by the peculiarity of this thought experiment's setup. So if we use n users, we have to write an n over 2 a lot of times down the road. Let's just write 2n therefore. So if there are 2 users, after 2 user, after 4 user, after 6 user, what's the chance that the next user would start a cascade? Well, the probability that there's no cascade after even 2n users is simply that this pair, they write down different public actions. Y1 is different from Y2, which means the third user is back to the same shoe as the first user. And these two users, this pair Y3, is also different from Y4 and keeps on going after n round of these. That means we want to say that the probability of no cascade after 2n people is p times 1 minus p. This happens for every pair. So this times multiply itself n times. That means we raise this to the power n. Okay? And the probability of having some cascade equals 1 minus this expression. And the probability of up cascade or down cascade, meaning all ones or all zeros, eventually after 2n rounds, is just half of the probability of having some cascade. Alright, now let's see what happens as n becomes large. We see that as n becomes large, this expression goes to 0. Because p times 1 minus p is some number less than 1. And therefore, the chance of having some cascade goes to 1. In other words, just wait long enough. If people think like this in this simple thought experiment, cascades is guaranteed to happen no matter what.